Last lesson we looked at potential difference in uniform fields. And of course we know that we make uniform fields by having parallel charged plates with a small distance between them. This lesson will look more at these parallel plates. They're so useful for so many applications that they have a name. We call them capacitors. Let's imagine two parallel metal plates, initially with no charge, and we start to transfer electrons across from one to the other. As the electrons move across one by one plate will become more negative and the other more positive. An electric field starts to build up between the plates. As the charge builds up, each electron is harder to move across and more work has to be done on it. Since we are doing work to make this happen, we are essentially storing energy in the field. We call that charging the capacitor. We can extract that energy later to do useful work by connecting an external circuit so electrons can return to the positive plate through the external wire. This is called discharging the capacitor. You can buy all shapes and sizes of capacitors, but the shape we will concentrate on is the parallel plate capacitor. It is so common that the symbol for a capacitor is a pair of parallel lines, as you can see in the diagram at the top right. Now you can see here that capacitors store a lot of energy. This is always a popular demonstration with classes. You can see a fair few of these examples on YouTube. So if ever your classes want to watch a watermelon being blown up, this is a perfect example. So as you can see, capacitors store lots of energy, and the important thing is that they can release it very quickly. Now we have to define a quantity called the capacitance. It's defined as the ability of a body to store electric charge. The capacitance C is given by Q over V, and because the sign doesn't matter, it is the absolute value of the charge Q over the absolute value of V. Capacitance is measured in farads, which is given a symbol capital F, after Michael Faraday. And like the coulomb, it is a very large unit, so we often measure capacitances in nanofarads or even picofarads, which is 10 to the minus 12 farads. The way a capacitor works is that you start with it connected to a voltage supply. This is what we see in the left-hand circuit here. The resistor is in there as well to limit the current. Now current can't flow across the capacitor because it has an air gap in the middle. So when the supply voltage is turned on, charge builds up on the capacitor until the voltage across the capacitor equals the voltage from the supply. This happens in a very short time. Then it can't charge any further, so the charge on the capacitor reaches a final value, and after that it stays constant. This is what you see in the graph at the bottom left. If we disconnect the capacitor from the power supply now, it still has charged plates, so that means it has stored energy. If we simply connect a wire from the positive plate to the negative plate, as is shown in the right-hand circuit, current will now run through the wire until the capacitor is completely discharged. This also happens quite quickly. So you can see that capacitors can act much like rechargeable batteries, except that batteries can provide current for hours, but capacitors give out all their energy quite quickly. Though you can see from the graph it doesn't lose charge at a steady rate, it actually discharges exponentially. A quantity called the time constant is given by that value RC, so R being the resistance and C the capacitance in that circuit. And that gives the time it takes to drop to about a third of its original charge. A large value for C will mean that the capacitor takes a longer time to charge up and to discharge. Just to give you an idea, a 100 microfarad capacitor with a 10 kiloohm resistor will take about 1 second to charge up and to discharge. Now we need to find the equation for the capacitance of a parallel plate capacitor. So let's have a look at the working. So we'll start by drawing our charged parallel plates. And we have the positive one at the top, negative at the bottom. So this is plus Q, this is minus Q. Now we'll look in the Z direction, we'll call it. And so we will start at the top plate at Z is 0, and the bottom plate we will call that Z equals D. So we'll call the area of the plates A, and the separation is D. And in between here we have a uniform electric field. And we're interested in the change in potential as we go from an initial point I to a final point F. First thing we have to do is to find the electric field. And we are going to use Gauss's law, remembering that in Gauss's law, E0 times electric field through the surface, which is the flux, is the enclosed. So that was E0 phi equals the enclosed charge. So we're going to pick our Gaussian surface. It's going to run midway through the top plate, down a little bit, come along under the top plate, and then back up at the sides. And we're going to label the side surfaces 1 and 2. This top surface that runs through the middle of the plate we will call surface 3, and the surface that's running underneath the top plate we will call surface 4. So we need to know what is the flux through all of these surfaces so we can add them up. Now for surfaces 1 and 2, the electric field that's only running vertically is parallel to the surface. So there is no flux through those sides. Now, surface 3 is inside a conductor. And inside the conductor you have no electric field, because if there is an external electric field, all of the charges that are free to move distribute themselves to oppose it. So again, you have electric field is 0, and so the phi is 0. So we're only interested in surface 4, and that has the electric field is perpendicular to the surface. So the flux is just E, which is a constant, times A, which is the area of the plates. So we have E0 times phi equals E0 times E times A is going to be the charge of the top plate. So that gives us that E equals Q over E0 A. Next step, we want the potential difference. So VF minus VI, and that will be minus I to F E times ds. Now, the path our ds is taking is, of course, in that z direction from the top to bottom. So that will be minus from 0 to d q times E0 A, and that's in the z direction. So that will be minus q being our constants here, E0 A, and that's just the integral of 1 times dz, which is just z, evaluated from 0 to d, Now at naught, obviously it's 0, so we just have minus Q D over E naught A. And then finally we can work out from that our capacitance. Now that is the voltage, so capacitance, that the absolute value of Q over the absolute value of V will be Q divided by QD over E naught A, which means times by E naught A over QD. Q's cancel, so we are left with the capacitance is E naught times A divided by D. So the bigger the area of the plates, the bigger the capacitance will be, and also the smaller the separation of the plates, the bigger the capacitance will be.